In our previous lectures, we have briefly discussed different levels of material structures, including atomic level, crystal structure, and microscopic level. So we know what parameters are characterize these levels of structures, as well as what mechanical and physical properties are defined by different levels of structures. The last portion of this course is dedicated to the different material science techniques which you have to use or you may use in order to learn more about different levels of material structures. So we will start today to discuss the widely used X-ray diffraction analysis, so which allows us to characterize the crystal structure of materials. On the next lecture, we will talk about transmission electron microscopy analysis, which allows you to go deeper inside the atomic structure of our materials. Finally, we will talk about the scanning electron microscopy, which is, I believe, the best way to investigate the microstructure of materials. So let's talk about X-ray diffraction today. Again, this screen shows you similar picture of crystal structure of materials, and we know that some 7 different classes of crystal structure exist, and these classes, they characterize by different parameters such as the despacing, for example, and I will give you a little bit more idea about despacing in the few slides. But the question is, how do we define what crystal structure we have? In other words, what phases do we have? Because it's very, very important to know what kind of phase composition of your materials. And so we are sitting now on the sizes on the order, let's say 10 angstroms and a little bit maybe above 10 angstroms, and X-ray diffraction technique is very nice approach in order to answer the question. So before we go to the details about X-ray diffraction techniques and talk a little bit about the history of the X-ray diffraction, I would just want to give you the general image, a general picture of the approach, and remind you about the so-called despacing. Indeed, so for example, you know, we may have a cubic structure of any kind of metal, for example. This cubic structure, so in this cubic structure you can find very many different planes which are characterized by the Miller indices H, K, and L, as you know this. These Miller indices, which correspond to any sets of planes inside any crystal structure, they related through the parameters of the cube. Let's say A, this is the size of the edge of the cube, and so-called despacing. Despacing is the distance between any selected parallel planes with the Miller indices H, K, and L. And knowing D, then by the very easily derived formulas which are presented on this screen, you can find the, let's say, geometrical parameters of your crystal structure. Now, for example, for cubic structure, you will find the length of the edge of the cube. For the tetragonal, hexagonal crystal structure, so where the parameters A and B and C may be not equal to each other, you will find the length of the A, B, and C in nanometers, and then comparing with the known data book parameters or standards, you can make your conclusion about what kind of phase you do have in your materials. First, let's refresh our mind about such phenomena as interference, which you know from the basics course of physics. You remember it was an argue between the Newton and Huygens about the particle or waves nature of photons of light, and you know the answer now on this issue, that indeed photons can behave as the waves under one condition and the particle on the other conditions. so about dual nature of photons. But for us now is more important so the wave type of behavior of photons, and the famous Thomas Young double slit experiments, where for the first time he observed the interference phenomena. So indeed, if we do have a screen and we will make two holes, two slits S1 and S2 in this screen with some distance d between these holes, and then we will organize some the beam of light with the same wavelengths, let's say monochromatic light, parallel coming to these slits. And then, owing to interaction between these beams on the screen, we will have the interference picture, namely, so you will see the sequence of extremely light and extremely dark regions. So this interference phenomena or can be mathematically treated, and you can find, for example, the distance between two slits S1 and S2 based on the analysis of the interference picture. That's the whole idea, so which can be used in order to, if you want to investigate your materials, if you imagine that instead of the two slits you do have actually the crystal structure, and the crystal structure is, as you know, it's very periodic, sequence of location of atoms with some distance between them, and you have to use some very special light in order to see this kind of interference picture, because as you remember, so the wavelengths of the used light in some sense or radiation should be comparable to the investigated, let's say, size in between slits, should be comparable with the characteristic size of the crystal structure. And in 1901, Wilhelm Conrad Röntgen, so he got a Nobel Prize just for the discovery of this kind of radiation, very strong radiation with the length from 0.1 nanometers, which can easily went through a closed black cartoon and hitting a fluorescent screen. And again, for us, it's even more important that the wavelengths of this kind of radiation is comparable to the size of the crystal structure. So having these X-rays in hands, Max von Laue, based on the idea explained by, let's say, Bravais, we already talked about the Bravais lattice. An idea was that indeed all crystal structure is nicely array number of slits, if you want. And by using X-ray, assuming and knowing that actually, so the wavelengths of the X-ray comparable with the distance between atoms in this crystal structure, so Max von Laue suggests that you can use X-ray in order to repeat, in some sense, these Young's double slit experiments, and to obtain the interference picture by passing the X-ray through the crystal structure of any kind of material. Then, based on the analysis of this interference picture, you should be able to make conclusion about the size of the crystals. And indeed, so it was obtained, and he got Nobel Prize in 1914, while Sir William Henry Bragg then in 1915 got Nobel Prize in order just to provide more simple interpretation for the Max Laue results. He just suggests that, and he assumed that the crystal planes, for example, we can see on this slide 3 planes with the d spacing d between them. The crystal planes reflect radiation as a mirror, and then he analyzed the kind of interference which should be obtained based on the interaction of this kind of beams after the reflection, mirror reflection from the different planes in our materials. And he derived very famous Bragg formula, and you can see this formula here. Next slide will provide you a little bit more details how one can derive this formula, but bottom line is that so if you know indeed the wavelengths of used radiation, and so you know you can measure actually the reflection diffraction angle eta, so on the screen, and having the maximum on the spot when the difference between the passes of the two beams reflected as a mirror on the two parallel surfaces, they will exist only when so the following Bragg equation stands. Just in order to, just because he provides this kind of information, just the right or simple interpretation of the deep physical phenomena, he got a Nobel Prize for that. It means that the most important thing in science sometimes is not so much to obtain new facts as to discover the new way of thinking about them, and that's have been done in the field of X-ray diffraction by Henry Bragg. So this screen gives you a little bit more idea how one can derive indeed this famous Bragg formula. Now again, the general statement is that the constructive interference can be observed only if the different impasses of two, in this case, beams, if this different impasses delta equals to the integer number of wavelengths, assuming that for sure we know the wavelengths of the used X-ray beam. And so it's very easy to obtain that this may happen only at reflection angles which related to the wavelengths and to the d-spacing between any parallel planes inside our crystal structure. 2d HKL sinus eta equals to n lambda, so integer number of lambda. And if it's so, then measuring the interference picture, one can calculate actually DHKL, and knowing DHKL and assuming the type of the crystal structure, it can calculate characteristic of any unit cells. That's the whole idea. Of course, so there is not one, but many parallel HKL planes exist in our material, we assume, and because of that, we can talk about the first order reflection, second order reflection, so it means that we expect to have not one, but several peaks which correspond to the reflection between these HKL selected planes. All right, so on this screen you have you can see the schematics of the power diffraction Bragg geometry. So what do we have? For sure, we do have the X-ray tube, which radiates actually the X-ray with the known wavelengths. We have our sample nicely located inside the XRD machine, and you have a detector which generally moves along our sample and detecting numbers of photons which it can be detected at very special diffraction angle eta. So actually that's it. The typical time for the obtaining the general information XRD pattern if you want from your sample is on the order of 20, let's say, to 40 minutes. However, if you want to go to more precise analysis of the crystal structure, including, let's say, grain, crystalline size, including strains which you introduce inside your material, this type of analysis can be as long as 20 or more hours. On the other hand, again, just for the general information, so now if you use the extremely strong cyclotron radiation at the X-ray source, so and linear type of detectors, which you can obtain the XRD pattern in some range of diffraction angles in the time span of microseconds. You have to remember this also. So idea is very simple. If you have a single crystal, and for example, in this case, 110 planes is just parallel in some sense to to the investigated conditions, optimized conditions, then we can expect so the diffraction peak obtained by detector 100 diffraction peak here. So while the other planes, which is 110, for example, they're not in the optimum position relative to the beam. In this case, we will not see the big peak from the diffraction from the 110 plane. It will be some kind of noise there. On the other hand, 200 is actually so the double distance as compared to the 100 peak, and then we will see also reflection peak from 200 with diffraction angle twice as high as compared to the 100 planes. So typically we do have a polycrystalline sample, and in this case the picture can be different as compared to the single crystal case. So because we assume that for the polycrystalline sample, every time we do have some percentage of crystals that are properly oriented to the diffracted beam, and so these crystals, they correspond to different sets of planes inside our materials, and in this case every time we will have some peaks corresponding to the diffraction from 100, 110, 111 and other planes, and then having information about the location of this peak. And of course this picture may happen only in the case of the primitive cubic crystal structure, as you will see just in a couple of slides. You can easily calculate the size of the cube, the size of the crystal, and then so make your conclusion what kind of material, what kind of phase do you have. So that's a typical diffraction patterns, which consists of very many peaks. So based on some, I want to say, knowledge, you have first of all decided to what HKL, to what planes so correspond this or the other peak, and then by using knowing formula and knowing of course the wavelengths of the used X-ray, you can calculate the crystal parameters of your materials, and that's just formula. So again, from the Bragg formula we can define the d-spacing easily, and then knowing what kind, or assuming what kind of crystal structure do you have, cubic, tetragonal, orthorhombic, hexagonal, monoclinic or triclinic, you can calculate the parameters of this structure. So the question is, or we can give you one example. For example, this is a cubic pattern, is the XRD pattern for the primitive cubic cell, that you may say that the first peak corresponds to 100, second peak corresponds to 110, third peak corresponds to 111, and so on so far. So that's so-called indexing patterns. So you can do it manually, and I suggest you every time for the first time to do the manual indexing of and manual analysis of UXRD pattern in order you can feel it by yourself and trust, you know, to the approach. However, you know that currently many software packages exist which are doing this job for you, but in general, if you want to go manually, you just indexing the HKL of the corresponding peaks, then you can easily find out the corresponding diffraction angle. Using Bragg formula, you will calculate corresponding d-spacing, and knowing that this is primitive cubic crystal structure, you will easily calculate so the parameter of the cube A by known relation between the d-spacing, d-HKL d-spacing, and the cube parameter. So that's general approach. It's not bad to know how find out the relation between the diffraction peaks, Miller indices, and lattice spacing. So then you go to the database, and this kind of all cards which shows you what kind of parameters or d-spacing or even diffraction angles correspond to this type of phase, and then you have to match your measured parameter with the parameter in the database. Of course, that again can be made manually or with the help of the software, and then you make a conclusion about the crystal structure of your material. Same approach you can use for the tetrahedral pattern, slightly more sophisticated, of course, relations between d-spacing and parameter of the tetrahedral in this crystal structure. Same for orthorhombic, so every time, so same approach, and this allows you to measure, to define the phase composition of your material. One exemption, very, very important one, it's again coming back to indexing. So in the case of the primitive cubic structure, there is no any restriction in the interference from any kind of planes inside the primitive cubic structure. So it means that indeed first one will be 1, 0, 0, second one 1, 1, 1, third one 1, 1, 0, third one 1, 1, 1, and so on and so far. However, in more sophisticated, in more difficult or more often cases, when we do have the body centered, or we do have the base center, or we do have the FCC phase center structures, so there is a restriction on the peaks, which is related to the interaction of the beams diffracted from different atoms inside this relatively complex cubic structure, if you want. And this table so demonstrate you what kind of restrictions you may have. Now, let's take just one example. The rest are the same. That in the case of the body-centered, so you may have a reflection only from the peaks for which H plus K plus L are even. So it means that, for example, you cannot see peak 1, 0, 0, because in this case 1 plus 0 is not even for sure. First peak which you can see will be 1, 1, 0. Again, you will not see peak 1, 1, 1, and so on and so far. The other restriction for other crystal structure you can see in this phase, and that you have to take into account when you're making indexing of the obtained XRD pattern. So that slide, in some sense, summarizes the whole idea of the lecture, so that XRD is an extremely useful approach, and with the help of XRD, you can define so the phase identity, you can define the lattice parameters of this phase, you can figure out if you do have crystalline material or you do have amorphous material, and even you can try to find out percentage of different phases, so-called quantitative XRD analysis, which is a little bit more complicated, but in any case, even percentage of phases which exist in your material. So what you cannot get with the help, what information you cannot obtain with the help of XRD is for sure, cannot, for example, make a conclusion about the elemental composition in your materials. So what information you cannot obtain with the help of XRD? First of all, you cannot talk about elemental analysis. You cannot define so how much, for example, lithium we do have in this sample, or iron, or so on and so far. In principle, you have to have some idea, so what kind of phase composition you can expect. You cannot try to answer only with the help of this technique with such complex questions such as tell me what this sample is. Only combination of the, let's say, electron microscopy with XRD so may answer this type of questions. So again, before we go, let's also talk a little bit about the space resolution. So typically the size of the sample should be on the order of several millimeters square, and the thickness of the sample should exceed about 100 microns. So penetration of the X-rays inside the sample is on the order from 50 to 100 microns. It depends, of course, on the composition. So it means that if, for example, you are analyzing with the help of XRD the coating, extremely thin coatings, let's say micron size coating or less, on the some substrate, for sure you will also feel substrate. You have to take this into account. So let me conclude that X-ray are electromagnetic radiation of wavelengths on the order of 1 angstrom, which is about the same size as atom, and of course the same size of a crystal structure. And starting from the beginning of the previous century, it's widely used in order to analyze the crystal structure crystal structure of material, and it's extremely powerful tool which does have many modifications, but we are not going in these details now. And in order to know that, you can go to the full lecture attached to this course. But so I just want to encourage you to use this analysis widely as even the first analysis on any kind of material. If you do have question, what phase composition I can expect here. Thank you so much for your attention.